Welcome to the 21st lecture of the course Turbulence. Okay. Before we proceed, let us recap a little bit of the previous class. So, what we learnt? We started talking about free shift flows. In the last couple of lectures we have talked about that. We started with the momentum equations, then went ahead with the order of magnitude analysis of these equations, and finally we could find a simplified version of the momentum equation. Then we considered the self preservation principle, and with that we could find the solution of the momentum equation, okay. And the solution of the momentum equation found to be f of xi equals to exponential xi square for alpha is equal to 1, if you can remember, okay. So, what is xi here? Xi is y by L, okay, and your what is f? F is defined u naught minus u divided by us equals to f of xi, okay. So, this is what we found in the last class, right, and along with this we also found another two relations, if you can remember, that is our So, this is the first solution we have got, and for self preserving wake we also found that how us will vary with respect to downstream distance, that is also we found in the last class, and that was if you can remember 1.58 theta divided by x to the power half, right. So, with variation of x or with increasing x, your us value will come down, okay. Us is the maximum velocity deficit at the central line of the wake, if you can remember, okay. So, let me just briefly draw that for. So, this is what is our, let us say, the wake, okay, and if you can remember that our velocity profile something like this, right. Okay. And this deficit was us, okay. That is what we defined as us, and L we consider a distance, okay, from the central line where this quantity this f of xi will be around 0.6. So, that is what we for precise definition, if you can remember, that L at a distance where the the value of this quantity is going to be about 0.6, right. So, this is what is our relation, and another relation, that means it says that how us in a turbulent wake will vary with respect to downstream distance x, that is what it says. So, downstream distance means this is what your y direction and this is what your x direction, this is what is the central line of the wake, okay. So, we have another relation, that L, okay, the cross stream length scale, how it will vary as you go downstream. So, that normalized by theta. So, if you see this particular value, this is 0.252 and this is going to be x by theta to the power half, okay. That means this particular length scale varies as x to the power half, okay. So, that means that L slowly increases as we go downstream, okay. All right. So, this is what the relations we could find in our last class, okay. So, today mainly we are going to consider some of the scale relations and the turbulent kinetic energy equations, okay, or its simplification for these particular solutions for a turbulent wake. And I mentioned in the last class that this particular profile is seen to match very well near the center line of the wake. It only slightly deviates about 5% towards the outer edge of the turbulent wake. Okay. That is what we have talked about in the last class. Okay. All right. So, now let us consider the Reynolds stress. So, what is this Reynolds stress? Reynolds stress, this can be written as this. Okay. So, we can consider the Reynolds stress is this. Now, we can find the value of del u del y. So, we know that u naught by u divided by us equals to f of xi, right. So, that means minus del u del y equals to u s, okay, and d f d xi d xi d y. Okay. So, that means this equals to u s f prime, let us call this as f prime, and this d xi dy, that means our xi is equal to what? Y by L. So, d xi dy is equal to 1 by L, right. So, that means this is divided by L. So, or we can write that del u del y is equal to minus u s f prime by L, right. So, now if you plug this in this particular equation, then we can write minus u v minus nu t, that is u s f prime by L, okay, or minus u v equals to minus nu t, okay, and let me take one u s L, and then it is going to be u s square f prime. Okay. So, this is what I can write, and this particular quantity is nothing but then R t, Reynolds number based on this eddy viscosity nu t. Okay. So, that means this is going to be u s square f prime R t. Okay. That is what it says, or we can say minus u v divided by u s square equals to, we can remove u s, we can equals to nothing but our f prime divided by R t, right. Now, when this quantity is going to be maximum, the value of this particular quantity is going to be maximum when f prime is going to be maximum. Okay. So, wherever that f prime is maximum, this is what is going to be Reynolds stress at that point is going to be maximum. F prime means what? F prime is nothing but your this shear, F prime is nothing but your shear. So, very important point here, that Reynolds stress is going to be maximum where the shear is maximum. Why is this so? Because when there is a shear, so that means what? There where your fluctuating velocities are going to be higher, okay, due to this shear. Okay. As a result, your this Reynolds stress is also going to be maximum near this, okay, maximum of this shear. Okay. So, this needs to be kept in mind, that wherever the shear, okay, mean shear is going to be high, your Reynolds stress is also going to be high, and your production is also going to be high. Okay. This needs to be kept in mind. Okay. All right. So, this is what we got. Now, you see what we can do, f prime we can find it out from this particular equation, right. F prime we can find out from this particular equation and plug it here. Okay. So, if you do that, so what is our f prime? So, that means, see, f is equal to what? Epsilon, sorry, exponential, okay, xi square. Okay. If this is so, then f prime is going to be what? minus xi exponential half xi square. Okay. This is what is your f prime. Okay. Now, where it is going to be maximum? Where f prime is going to be maximum, to find it out that we have to find the double derivative of this quantity and make it equal to 0, so that we can find the condition where it is going to be maximum, right. So, to find the, if we find the double derivative, so that means we have to make the derivative of this quantity, okay, f prime to be 0 for maximization, right. So, now d xi f prime is equal to what? Minus xi epsilon exponential half square, right, equals to 0, okay. Or you see, take the negative sign out, exponential half 0, or you see minus, so exponential half xi square, then differentiation of this is going to be xi square, then epsilon exponential, okay, equals to 0, okay. Or what you can do, that means it is going to be xi square minus 1 into your essentially f is equal to 0, okay. So, it gives, this gives that f prime is going to be maximum at this, okay. This is the condition, okay. So, that means it says this quantity, this Reynolds stress is going to be maximum at xi is equal to 1, okay. At xi is equal to 1, this quantity is going to be maximum. Then if this is the case, then what is the value of this quantity? That is what we have to find it out, right. So, to find out this quantity, let us do one thing. F prime is this, let us see the maximum value at xi is equal to 1. That means, at xi is equal to f prime at xi is equal to 1 is equal to what? Minus exponential half, right. So, that means this is going to be plus. So, this is going to be minus exponential half by RT, okay. So, this is what this relation gives. So, let me just do it here, okay. So, that means minus uv bar us square max equals to, we get half RT, and RT, our experimental observation shows that RT is essentially 12.5, okay. With this condition, then we can find the value of this. So, to get that, so what we can do, little more simplification we can do. See, after that xi is equal to 1, that u and v can be approximated as the correlation of u and v can be approximately 0.4 into ut square. This quantity, okay, can be replaced with 0.4 ut square, knowing the fact that that uv correlation for turbulent wake is actually 0.4 into ut square, where ut is so let me just finish this writing us square equals to RT, okay, and here your ut is defined as ut square is defined as 1/3 ui bar. That is what your ut as for the definition. Okay. Now, from this what you can find, if you just go ahead with the so this is this value correlation minus uv we are replacing with this. So, from this we can find that that ut equals to we can find, if you go ahead with the algebra, then this is what you are going to find. Okay. So, this is what, so that means ut or RMS velocity in the wake is given by this relation approximately. Okay. This is what is the relation for RMS velocity, right. Now, this is one thing. Okay. We need to find out another relation. So, another relation we have to see here, see what is going on. Okay. See what is happening here. The wake is expanding in this direction. Okay. So, now let us say somebody is moving with the free stream velocity u naught. Somebody is moving with free stream velocity u naught, then what he is going to see? He is going to see that each and every x location this L is different, because L is a function of x. Okay. That is what this relation shows, L is a function of x. Okay. So, that means when somebody is moving with this u naught velocity, what you will see? You will see there will be a growth of L with respect to time. Okay. That means to that particular person who is moving with the free stream velocity u naught, he will see that L is increasing with time. Okay. So, that means if you would like to find out dl dt, how we can find that? Okay. So, dl dt in that case then can be written as, you see, I can write dl dx into dx dt, okay, and this I can write u naught into dl dx. Okay. So, that means this particular dl change of L with respect to time when somebody is moving with the wake at velocity u naught, okay, can be replaced with this particular relation. Okay. So, now how to calculate the value of this quantity? That means we have to first know the value of this quantity, then we should be able to calculate the value of this, right. So, that means dl dx, see dl dx can be obtained from this. We can find the dl dx from this equation, right. So, from this equation, let me do it here. So, from this particular equation, okay, if we differentiate this equation with respect to x on both this side, what do we get? So, we can write dl dx equals to 0.252, this is going to be theta to the power half, and this is divided by 2 will come here, and this is going to be x to the power half, okay, or dl dx 252, and you see then this can be written as theta by x to the power half. So, now you see this equation, theta by x to the power half equals to this divided by this divided by 1.58. Okay. So, that means this particular, from this we get dl dx equals to 0.252, and this quantity can be replaced with us by u naught into 1 by 1.58 0.58. Okay. So, this is what we can replace with. So, or we can write u naught dl dx equals to u naught dl dx. If you calculate this is going to come about 0.8 okay, US. Okay. So, that is what you are going to get. That means, your hence your dl dt equals to dl dt equals to your 0.08 US. Okay. So, this needs to be kept in mind, right. So, this velocity, see both the velocity ut as well as dl dt, this is also sort of velocity, both are proportional to US, which is expected in the case of self preserving wake. Okay. So, these are the relations. Now, there are two time scale we can find it out. Okay. So, these are the relation for the velocities. Okay. So, let me write this velocity here itself. So, these two dl dt equals to 0.08 US. Okay. So, these are the two relation we have got. Now, we will work with time scale. Okay. Okay. So, there are two time scale we will try to find it out. One time scale characteristics of turbulence. Okay. So, characteristic turbulent time scale let us consider to be Tp. Okay. Time scale. Okay. How we can find or how we can estimate this particular time scale from the known value. Okay. So, this time scale Tp can be defined as half ui bar divide uv bar del u del y. Okay. So, this is what we can define this Tp. Okay. Now, you see, if this is the definition, that means this is what the energy and this is the rate of production. When energy is divided by the rate of production, it gives a time scale. Okay. The time scale of what? This time scale, the energy which is kind of from this larger scale coming to the smaller scales, that particular time scale we get it from this particular ratio. Okay. Now, can you estimate these value in terms of US or in terms of any other known variables? Okay. So, that is what our objective. Now, if you see what is ui and ui, you see ui and ui is nothing but your 3 ut square as per the definition, because ut square equals to 1/3 of ui into ui, right. So, that means here we can write, that means this is equal to half 3 ut square, and this value, this particular value we have to replace with the value we have got earlier, right. So, these other things we have removed. So, now you see what we can do here, that uv, this we can approximate it as what 0.4 ut square, and this del u del y. So, del u del y we did it, once again we have to do it because we have removed it. So, let me do it here. So, we have to calculate the del u del y, but we know this u s is equal to f of xi. Okay. That means minus del u del y equals to u s f prime and dxi dy. That is what it is, which is nothing but your u s f prime and dxi dy is equal to by L, right. So, this is dxi dy is nothing but your 1 by L, right. So, that is why this one is this, that means del u del y is equal to minus u s f prime by L. So, you replace this value. So, that means del u del y, here we can put what minus. So, this minus, so this is equal to this. So, minus will be there, this particular minus, and that is going to be your what u s a prime by L, right. That is what we are going to get it here. So, that means you see ut square will cancel, that means Ly. So, Tp is equal to essentially we are, so Tp is equal to, let me write it here. So, Tp equals to, what do we get then, 1.5 divided by 1.5.4, right, and this is L by u s f prime, right. So, that is what we get. Now, we have to put the value of that a prime. Okay. So, a prime is what, if we consider, so a prime half xi square, right. So, a prime is nothing but your minus xi f of xi. Okay. So, or we can write exponential half xi square, right. So, the maximum, if we consider the Tp, the minimum Tp, that means minimum Tp is going to be when f prime is maximum. F prime is maximum at what location? When xi is equal to 1, that is what we have noticed, right. So, that means the maximum value, so the maximum value, so you see that 1.5.4 you are here, there is a minus sign we have missed. Okay. So, there should be a minus sign here, there should be a minus sign here. So, this the moment you are considering this minus sign for this, so this is going to be positive then, and the maximum value of it, this is L, and this is going, maximum value of it is going to be exponential minus half. Okay. That is the maximum value of f prime into u s, right. So, that means this particular value is going to be 6, approximately 6.2 L by u s. Okay. So, the value of this is going to be 6.2 L by u s. Okay. So, that means your time scale of turbulence is in terms of L and u s is this. Okay. Now, we can find another time scale of flow development. Okay. So, this is your characteristic turbulent time scale. Now, we have to figure it out another time scale, let us say that is considered as T d. This is known as time scale for flow development. Okay. So, this is what we have to calculate now. Okay. Now, how we can define this TD? Okay. So, that is what we have to consider. Okay. So, now this TD is defined as, okay, TD is defined as L by dl dt. Okay. This is a time scale of development of wake, means the time scale at, the scale for development of the wake is divided is given by L divided by dl dt. Okay. Now, dl dt we have got it already, dl dt, right. So, you see, so that means this is going to be L divided by dl dt is given as 0.08 US, right, that we have already calculated, and this equals to, you see, what do you get? So, 100 divided by 8, which is 12.5 L by US. Okay. So, now we have two time scale, one is this, okay, the development time scale. Development means the wake, how it develops as we go downstream, means the wake is slowly coming towards the irrotational flow side. Okay. So, that means the wake is entraining, okay, it is entraining the irrotational flow, and that time scale is this. Okay. And another is your TP, which is turbulent time scale, which is approximately 6.2 L by US. Okay. So, these are the two time scale in the flow. Now, if you see this TD divided by TP we consider, which will come approximately 2. What it says? At the rate, turbulence wake develops in the downstream direction, or the ratio of the development with the the turbulence generation, or at the rate or at the time scale the turbulence is generated, okay, or turbulence is cascaded down to the smaller scales, ratio of these two time scale is 2, means at what rate turbulence is going to be generated at a particular point, at the same rate it is not going to be convected downstream. Okay. So, since the ratio is not 1, that is the case. At the rate the turbulence is generated at a particular point, at the same rate it is not convected downstream, okay, something like this, or it is not at the same rate, it is not taken away from that point. As a result, it with time it slowly, the turbulent wake is slowly expanding towards the irrotational side of the flow. Okay. What I would like to mean, the time scale it takes to generate turbulence, okay, at a particular point, at the same rate, it does not get convected, means it takes, it quickly generates, but while getting development or development time scale is much larger, means it takes almost twice the time the turbulence is generated at that at a time scale at that particular point. Okay. As a result, this wake is slowly sort of developing, means it says the turbulence is not in equilibrium, okay, or turbulence is not in or never in equilibrium, but still the self preservation is happening because their ratio, okay, that at the rate the turbulence is generated and at the rate this development is happening, the ratio keep pace, means this ratio is constant, means the time scale the turbulence is getting generated and at the time scale it is getting propagated, they are sort of proportional. Okay. That is why this self preservation works for this particular case. Okay. So, this is one point I would like to make for this particular case from the solution whatever we have got for the turbulent wake. Okay. Now, the next particular topic we would like to come, that is our turbulent kinetic energy equation. Okay. Okay. Now, we know the kinetic energy equation, turbulent kinetic energy equation. I believe that you know all this. So, let me just write this equation. Okay. So, this is how what is our general turbulent kinetic energy equation, which is applicable for all the cases. Now, here we are going to approximate this particular equation for turbulent wake. Okay. If we go ahead with this approximation, okay, and see this particular this is u z it should be. Okay. So, that means this particular term, which is convection basically, or it can be called as advection as well. For 2D turbulent wake, we have two part u1 del x1 plus u2 del x2, right. These two, so u2 is 0. So, that means the second part is 0. So, u1 is going to be there. u1 is what? Is the local mean velocity, and local mean velocity we have showed in the previous classes can be written as u naught. So, that means this particular quantity, if we denote this particular quantity as q, okay, then this particular quantity we can approximate as u naught, okay, del half, this can be called as this, okay, ui into ui is equal to q square, which is nothing but half of the kinetic energy. So, this is q and this one del x, x1 means just x in this particular case. Now, we have already found that this viscous transport is negligible as compared to turbulent transport and pressure transport. So, we can forget this particular transport term, then transport term will have only two, that pressure as well as turbulent transport. Okay. Now, this also j, okay, j means for summation j is equal to 1 and 2, okay. J is equal to 1, this is negligible because we are considering almost parallel wake flow. So, in that case the variation with respect to x with transport of the transport term can be considered to be negligible. Then variation with respect to cross stream derivative y is only going to be there. So, in that particular case, then the transport term can be written as what? Del y, and let me, that u j is going to be your v. So, p v by rho bar minus, you see this half. So, this is half q square bar, okay, and this is your V. Okay. That is what is your turbulent transport term for this turbulent wake, and this is our dissipation, okay, and this is our production. So, in this particular case use that Reynolds stress, that is minus uv, okay, and this particular case only one shear term that is important here, that is del u del y. Okay. So, that means this particular term is going to be for turbulent wake is this, okay, minus the dissipation term, let us call it epsilon. Okay. So, this is what is our equation. Now, this equation once again we can simplify little bit this equation, let us do it. So, our this equation this particular equation we can write as u naught. So, left hand side we can keep it as 0 minus this is u naught del half q square bar del, this is y, sorry, this should be not y, this should be x. Okay. This should be x plus, not plus, minus, let us take the production term here, okay, minus your transport term. Okay. Transport term can be written as del y, v can be taken as common, and this can be written as p by rho plus half q square bar, okay, minus epsilon. Okay. So, here you see this bar we can instead of distribution you can take a single one and take the v out, okay. Then this is what we will get it, okay. The minus will come out, then this is what we can write it, right. So, and this is your dissipation. Now, so let us call this, so this is what is your simplified turbulent kinetic energy equation for turbulent wake, right. Let us call this is advection term A, okay, and this is production term P, this is transport term T, and this is your dissipation term D. Okay. So, there are 4 terms in this particular case. Okay. So, can we now estimate this APTD, okay, in terms of known, in terms of that F and J which we already found for the case of turbulent wake. That is what is our main intention. To do that, first we will consider Reynolds stress. So, minus uv, okay, that can be written as nu t del u del y, right. Now, nu to del u del y again minus nu t, what it came us by us by L A prime. This is what we got it, right. So, this is what we got, and here your nu t. So, essentially this can be written as nu t by nu t by your us L us square by A prime. Okay. Just let me check whether I am doing it correctly. Okay. So, u naught minus u divide us f. So, minus del u del y is equal to us f prime prime by L, right. So, this is fine. So, that means I am putting the value of this. So, that is it's going to be US F prime by L. So, del u del y minus US F prime by L, right. So, that means this is going to be, sorry, there is a mistake here. So, that means this is going to be your nu t US F prime by L. Okay. This is what it is, and this can be written as nu t by US L US square, sorry, this is F prime, okay, F prime, right. So, this equals US square F prime divided by RT, right. Reynolds number based on that eddy viscosity, right. So, this is what you got. Now, you see we expect that this and your kinetic energy Q is going to be closely related. Okay. Now, this one, you know, we can write this as let me write in the next line. So, or u v equals to minus u s square F prime divided by R t, okay. Or you see, or what you can write this, you know, as I said, if we consider this minus u v is well correlated after j is equal to let us say 1, then this is u t square, okay, is equal to minus u s square F prime by R t, right. Now, u t square by definition is what? U t square by definition, u t square is equal to, you know, by definition q square bar divided by 3. Okay. So, this equals to minus u s square F prime by R t. Okay. So, where we are? We are here. So, what is this? It is going to be, so we have to find out the value of this. So, this equals, we can write minus, okay, 3 or 30 divided by 4, 30 divided by 4 and u s square F prime by R t, okay, or this equals to minus, this is 7.5, right. This is going to be 7.5 u s square F prime R t, right. Okay. So, you see, if we now, you know, see the variation of this quantity at a particular position, you know, which you can do it because you see F prime which you can replace, okay, F prime can be replaced from our solution, right. So, then what we find, what can be found for this, you know, particular, you know, q square, how it varies, that can be plotted. Okay. this is y axis, this is 1, 2, 3. Okay. So, if you see, this quantity is going to be maximum somewhere where this f prime is going to be maximum. So, f prime is going to be maximum somewhere at j is equal to 1. So, that means this variation is going to be something like this. So, this is q square bar, the way it varies. Okay. But although this equation is showing that variation should be something like this, but experimental observation shows the variation should have been something like this. Okay. So, here what is the problem? The problem is due to the symmetry of the function f. So, if you see the function f, if you can remember that how f of j, if you see f of j was coming something like this. This is what is your f of j. So, f of j symmetric function about j is equal to 0. So, if you have a derivative of this function, then that is going to be 0 at j is equal to 0. Okay. So, therefore, this q square is going to be 0 as per this equation. Okay. So, which is not which needs to be carefully handled, because we consider this here the u v equals to 0.4 into u t square. This assumption is fine beyond j is equal to 1. Okay. Before that, this needs to be carefully considered. Okay. So, that is the reason that this is what we get as per this equation, but experimental observation shows this variation. Okay. All right. So, now you see we got the variation, or that means we got an expression for this, right. We got the expression for this, okay, in terms of some variables which can be obtained from the solutions, right. So, the point is here, you see, that means this particular quantity, this is in terms of q. So, it shows how it varies, okay, or here. Okay. So, that means this particular quantity, okay, in terms of q. Okay. So, this particular quantity in terms of q can be found from this in terms of q. Okay. Then this particular quantity as well can be found in terms of our solution. Okay. And this particular quantity is the problematic. So, this particular quantity is C, what it is? It is V, it is a correlation between V variable and the variable inside the bracket. Okay. If we forget the special term, then we can consider actually this particular correlation like your u v, how as per the mixing length theory, how do we express your this one u v means Reynolds stress nu t into gradient of u velocity. So, in this case what we can do, that v into this quantity can be approximately or crudely expressed as nu t into gradient of this quantity, this quantity q square. Okay. So, what I am saying, that considering the mixing length hypothesis, what we can do, this particular quantity can be considered as, so V half q square p by rho, this particular quantity we can approximate nu t q square bar del y. Okay. So, that means this quantity can also be approximated using q. Okay. So, you see in this particular equation, this is q, this also can be considered as function of q. If you see here, Okay. If you see this uv which is 0.4 ut square can be considered, and this can be considered as your this f prime, okay, from the expression of f. Okay. So, that means except dissipation all this term can be expressed in terms of q square, for which we know the mathematical expression. Okay. So, if we now calculate the normalized value of this quantity and this quantity, sorry, and this transport quantity q t, sorry, this transport quantity this, then what we can find the I do not have enough time. So, let me just quickly find the final expression, okay, and I want you to check all these expression at your hostel room. Okay. Take this as an assignment. Okay. So, that means if you consider your advection term. So, advection term advection term A, let us say A L R T divided by US cube. Okay. This will come as 0.3 f xi 3 minus xi square. Okay. This is what it will come. Similarly, your L P R T by US cube will come as f square xi square, and your L transport term R T US cube, these are the consider these are sort of non-dimensional value of advection, production and transport, okay, which is exactly is this 3 minus xi square. Okay. So, that means with these solutions we can approximate the non-dimensional value of the advection term, then production term, and then your transport term. Okay. Now, if we plot these, how do we get it? Let us see. Okay. Okay. Let us plot that. Okay. Okay. So, this is the production term, okay, the variation of the production term. Then this is what is our dissipation term, and this is the transport term. Okay. This is what is our transport term. So, essentially this is transport term, but it should be dotted. Let me come back why it should be. Okay. This is our approximation, and this one is our advection term. So, okay. So, this is, so this one is advection term A, this is your production term P, okay, or let us use this color only, and this one is your transport term T, and this one is your dissipation term. Okay. So, now we have to argue why this particular plot is like that. Okay. So, you see we considered that our UV kind of will be well correlated or can be expressed as 0.4 UT square after epsilon is equal to after xi is equal to 1. So, this axis is xi. So, this is 1, this is 2, this is 3. Okay. So, you see this transport, you see in the in the outer side of the wake, what it is showing that the energy it is transported from the center towards the outer side of the wake. Okay. So, this is what this term shows somewhere here, and whatever it is transported means it is trying to transport us towards the outer side of the wake, means our wake is like this, right. Our wake is this, and so this outer side means this side. So, this plot you can consider at a particular position, at a particular x position, and you are plotting with respect to xi, right. So, what it is showing this particular outer, so this particular term here somewhere here shows that kinetic energy is transporting from the center towards this side, means it is trying to go towards the irrotational side. So, this side is irrotational side and this is the rotational. Okay. So, inside the flow is turbulent. So, it is a rotational, outside the flow is not turbulent. So, the flow is considered to be irrotational flow outside. So, that means that this particular term, so transport term is trying to carrying energy from the central line towards the outer side. That means that wake is actually propagating towards the irrotational side, means that irrotational flow is entraining inside the turbulent flow. Okay. That is what it says. And whenever it is doing so, what this advection term, what it is doing, whenever this energy is transport term is carrying energy from the central line or towards from central line towards the outer side of the wake, that that advection is trying to take it in this direction. Okay. So, that is what they are sort of in balance, that is what these two things shows. But beyond this particular point is basically 3. So, beyond this what it is happening, this advection term is depositing that turbulent kinetic energy, and the transport term it is transporting towards the outer side. Okay. Within inboard of this particular point, which is actually about 1.7, okay, xi is equal to 1.7, inboard of this within these, that is what it is happening. Okay. Okay. And production, if you see production from this, if you see production, so this production term actually if you see this production is all right from this equation, because at production at the j is equal to 0 should be 0, because shear is 0 at that location. So, production should be 0. So, production can be said that will vary like this, and production is going to be maximum where the shear is maximum. The shear is going to be maximum where your j is equal to 1, that is what we have found from the velocity profile, keep it in mind. So, production term is going to be maximum here. Okay. Now, advection, if you see from this particular point, so advection beyond, advection with increasing beyond j is equal to 1 with increasing j is going to reduce, okay, like that, and at this particular point is going to be negative. Okay. So, from this point onward it is trying to deposit the turbulent kinetic energy, okay, towards that side, outer side, and this turbulent transport is going to somewhat balance it. That is what you can see here. Okay. That is what you can see, this term and these term are equal. Okay. So, now and here you see what is happening at this particular position, your actually production is equal to almost dissipation. So, production is decreasing beyond this j is equal to 1, and dissipation is also decreasing towards the outer side of the turbulent wake. Now, the point is here, what is going to happen in board of this j is equal to 1? We do not know for advection as well as transport as well as dissipation. Dissipation we can say that since near the central line turbulence is highly mixed, we can expect that dissipation will be higher as you are approaching towards the central line of the wake. Okay. So, that is what that this particular line shows. This is kind of our from this particular argument, this has been just extrapolated from this line. Okay. So, this extrapolation as per the argument that since near the central line of the wake turbulence is well mixed, so the dissipation should be increasing, that means it should increase like this. Okay. What about advection? For advection you see from advection, if you see that your experimental advection term, it is a advection term, what advection is a actually advection, if you see where our advection, so that equation I have removed. So, advection is going to be increasing beyond this point, because it is expected, advection is expected that it will be bit high near the central line of the wake, right, because if you see towards the central line of the wake, the value is this, and your what is this advection term, u naught into gradient of half q square bar del x, right. So, although this particular approximation says that it is 0, but this is due to the symmetry which is not correct. So, experimental data shows this. Okay. That means, this gradient of this particular quantity is not exactly 0. As a result, the advection term is going to survive, advection term is going to survive, and it will slowly, it can be expected to slowly increase, okay, or it is expected to increase and is expected to be maximum at the central line. Okay. If this is the case, then you see if and production is as it is, if advection is this and your dissipation is this, then your transport term has to vary like that to satisfy the turbulent kinetic energy equation. Okay. So, that is what can be said from this particular equation. Okay. And this particular estimate which we found from these solutions approximately follows the experimental observation. Okay. But for accurate case we have to consider the intermittency function, because as we said in the previous class that intermittency is 1 around the central line, but it does not become 1 towards the outer side of the wake. That means, you need a correction near the outer side. So, there where there will be some deviation, okay, with respect to the actual experimental observation. Okay. So, for further time is not there today. So, for further discussion on this or further understanding of this particular thing, I would like to refer the book Tenikens and Lumley. Kindly go to that book Tenikens and Lumley, and the better argument about this variation has been given in that particular book. Kindly read that. Okay. In case any trouble, we can discuss. Okay. Okay. Thank you. We would like to stop it here for this class.